Hello all, glad to be here. Welcome to this talk on using high-performance data processing in Python. Specifically, we're going to be applying that to doing some algorithmic trading. Just a little bit about myself beforehand. I'm a software engineer. I work for a New York-based algorithmic trading firm. So what we do is we build mathematical models to predict the prices of stocks and then try and build automated trading algorithms on top of that. What I do is I build our scalable data processing infrastructure. So we use hundreds of data sets to try and predict stock prices. And we need easy and fast ways to ingest all these different data sets in different shapes and sizes. And I'm also responsible for building the real-time trading systems that actually execute our trades on the market when our models have decided what to trade. So I'm primarily a Python and C++ developer. I'm trying to remove that C++ part and replace it with Rust because C++ is a pain in the ass to use. But anyway, about this talk. So as we all know, Python is a hugely popular tool for data analysis. That's the whole point of this conference, for example. A JetBrains survey last year showed that data analysis is now as popular as web development in Python. So half of all use cases in Python are now data science, which is a very different landscape to what it was, say, 8 or 10 years ago. And why is this the case? So as many of you know, it's because it's suitable for research. It's high level and easy to use, doesn't require advanced programming knowledge, and it enables researchers to write very complex things very quickly and iterate on ideas very quickly. But unlike a lot of its competitors, like MATLAB, for example, it's also a general purpose language that's useful outside of data science. This means that you can just take your code from research and easily, with very little effort, slot it into a production system, rather than have to re-implement everything from MATLAB in Python, for example. So that's the Python strength, is that it's suitable for both use cases. You can iterate on ideas quickly in research, but you can also take those ideas and deploy them in real-life systems with very little, if any, extra effort. So the issue is Python is slow, or at least pure Python. Python is not meant to be a fast language. It's meant to be an easy, high-level, easy-to-use language. Any benchmark that you actually do against faster languages like C or C++, Python will always lose out. Which means actually it's bad for research, pure Python, because it means that you're iterating very slowly because all the calculations you're doing are taking hundreds of times longer. And it's actually bad for production because you can't run time-sensitive data processing tasks without actually having to go with a faster language. So the solution is to use Python's data processing ecosystem. What we're going to focus on here is Numpy. I know many of you have already used Numpy, but many of you might not know how it actually works internally and why it's so fast, which is the purpose of this talk. And as many of you know, Numpy is the heart of scientific computing in Python. It stores and operates on C structures to avoid the slowness that Python has. And it's the foundation of a lot of packages like NumPy, Pandas, and so on, which I'm sure you all use on a daily basis. So our focus is to show how to use NumPy to process numerical data, explore how NumPy uses vectorisation to dramatically boost performance while keeping the productivity that Python gives us. We're going to be building an algorithmic trading strategy using stock pricing data. We're going to be processing that stock pricing data in pure Python, speeding it up using NumPy and vectorisation, and then speeding it up even more using another tool called numba. The final optimized solution will be almost 2,000 times faster than the original pure Python implementation. So let's do it. Let's make some cash. We're tired of working for the man. We're tired of slaving away in a company as just a corporate software developer. So we've decided we're going to use our skills to build an automated trading strategy and make ourselves a lot of money. The data we're going to use is a publicly available data set of 7,000 plus US stocks. This is pricing data for these stocks every day from 1962 to 2017. This data set is just a collection of CSV files where each CSV file represents the full pricing history of a single stock. So one of these files, for example, the one for Apple, AAPL, contains 2 columns, the date, and then close, which is the price of that stock at the close of the market on that date. So a very simple data set. And if you plotted one of these CSV files, you'd get what you'd expect. A stock charting graph, and as all stocks have mostly increased a lot over the past 20 years, you get this massive jump at the end. So the data set is very small. This data set is only a gigabyte in size. That's not very big at all. So why is this going to take so long to process? Well, it's because we're going to be doing some very complicated calculations on that data. So our goal is to build a program that generates a list of trades to make. So every day, our program will take pricing data, historical pricing data, from before that day, and then generate a single trade list, which is the buy and sell orders to send to the market. Disclaimer, the strategy we're about to do is extremely basic. This actually did work in the 90s and early noughties. This won't work anymore because everyone is doing algorithmic trading. So you need to be a lot more complicated than what we're about to do. But the good news is that this strategy does reflect the high-level structure of how real trading strategies actually work. So the type of trading strategies we run, this is the type of structure that we actually use. So the strategy that we're going to use leverages two fundamental behaviors about stock prices. The first is that prices revert to the mean. Now, you can imagine any time series where a time series, particularly ones like stock prices, are very noisy. So you get this like up and down notion, but then it's jittering around some kind of general trend. So even if a stock is generally going up, it's going to be bouncing around that sort of general upward trend. So, for example, the moving average might be this straight line over time, but the actual real price is jumping up and down, like on either side of that moving average. So, in other words, if a price drops below the moving average, we expect it to revert back to the moving average eventually because of this whole notion of it reverting to the mean over a period of time. So, if we consider the stock's returns, which is the change in price, not the absolute price, for example, we can calculate that by taking the price of a stock today, subtracting it from the price yesterday. And if we look at this graph, which is 2 weeks worth of pricing data or returns data for Apple, this graph represents the changes in the price of the Apple stock. So you see it drops $2 and then increases $2 and so on and so forth. The orange line is the moving average of the change. So what you can see is that it's generally zero. This particular one is slightly below zero. But what this means is that often you're just kind of bouncing around a mean because if you go down $2, you inevitably end up coming back $2 or close to it because of this moving average being zero. So a mean reversion trading strategy is basically you buy and sell a stock when its returns exceed a certain threshold away from the moving average. So as an example, suppose you have $90,000 to trade with. Suppose our threshold is $1. So when the price change is greater than $1 away from the mean, from the moving average, then we decide to buy the stock. We buy the stock because we expect it will revert back to the mean, which means that it will go up in price again. So we're buying low and selling high. So if we just always make sure when we buy these stocks, we sell after just exactly 1 day, regardless of what happens, then we do something like this. The next day we sell, and because the price has reverted back to the mean, we've made money. We repeat this process every single time we go beyond the threshold, and we eventually get these sequence of trade pairs, so these buy and sell pairs. Some of them make money, some of them don't. The key here is that you make more right trades than wrong ones, so you've guessed that it's reverted back to the mean more than you've incorrectly guessed that, and then you make money. So in this case, in these 2 weeks, we made a 2% return on investment. Not bad. But the problem is the price might not actually revert back to the mean. So there's this opposing notion of momentum, where a price might increase and then keep increasing, even accelerating rates. So rather than going up and then going back down, it's actually rallying and it's suddenly going very, very high. And if we try, or very, very low, and if we try and use mean reversion, we'll lose money because we buy low thinking it's going to increase again, and then it doesn't. So we sell even lower. So we just keep losing and losing money. So we don't want to do this. We want to avoid trading during these momentum phases. So we leverage the second behavior of stocks, which is that stocks are correlated. So as an example, if we plot the returns of Apple, the change in price of Apple and Amazon, you see that these time series are very similar. They're both big tech companies, so they both correlate very well with each other. When one moves, the other one tends to move. Similarly, Apple is actually correlated with the whole US stock market. So if you take the top 500 US stocks, whenever it moves, Apple tends to move as well. Sounds pretty obvious, I know, but this is actually a very powerful and useful piece of information that we can use to avoid trading during these momentum phases. So we use stock correlations to detect these phases and only use mean reversion when we think that stocks are hovering around the same price and aren't fundamentally going up or down over long periods of time. So basically, what this means is we take these, for all 7,000 stocks that we're going to trade, we're going to take the returns of that stock, the historical returns, we're going to combine it with the correlations that that stock has with all the other stocks, all the other 7,000 stocks, and then we're going to merge this into a time series called the unexplained stock returns. And then we apply mean reversion to this adjusted return time series. Now, the unexplained stock returns represent the movements in the stock price that we can't explain by other market movements. For example, if Apple decreases in price, but other tech companies don't decrease in price, so there's not this general market downturn, we can't explain the decrease in price. We don't think there's a real reason that the price is actually fundamentally decreased. So we assume that it's noise, and it's going to revert back to the mean, and we'll go back up again. So since only Apple has decreased, but all of its correlated stocks haven't decreased, we assume mean reversion, buy, and then sell the next day. This is the hardest step. Very, very hard. In fact, this is by far where all the magic comes in terms of making money. The most basic solution you could do is using PCA and linear regression to perform this process called residualization, which generates that unexplained stock returns time series for all of these 7,000 stocks. We don't have time to go into detail on how exactly these work here. Just remember that we are using these techniques to generate these unexplained returns, and actually this requires a lot of calculations. So if we actually try and implement this in a pure Python program, what we want to do is we want to run a simulation where every weekday, just before the US stock market closes, we calculate the stock's daily returns for the past year. We calculate the correlation of every single one of those stocks with every other stock. So that's about 7,000 squared correlations. And then we use the correlations and returns to do this, to get this unexplained stock returns, buy and sell, decide what buy and sell orders to make, execute the buy and sell orders, and then wait for exactly one day. We're keeping this very simple. We wait for just one day, and then we get rid of the stocks that we bought. We sell them all. So we're going to simulate how much money we make, and we can use the pricing data that we already have to do this. Our range is going to be 1990 to 2017. So 2017 is where this data ends, so we're just going to leave it at that. And we're going to write the strategy in pure Python. I don't have time to go into the implementation, but essentially it's pure Python. It's using various built-in Python C routines where necessary, but it's not using any kind of Numpy or any data processing library on top of just using built-in Python stuff. So the result is we actually make a lot of money to begin with. So from 1990 to 2001, this plot is the cumulative returns. So overall, if we put in, say, $1 million at the beginning, we're making about 16% on that million, which isn't bad. So that's pretty good. But as 2001 onwards occurs, we actually start to lose money. So what's happened here is that other people in the market at this time have actually started building way more sophisticated algorithms than this. So back in the 90s, no one was really doing this type of algorithmic trading, or at least to the same scale that they do now. So it was easy to kind of game the system and make a lot of money with very simple algorithms. Whereas now it's not. And so what's happened is we're competing against even smarter algorithms from 2001 onwards, so we're actually losing money. And that sucks. You know, that's not ideal. This stuff is hard, so you're not expected to actually succeed first time around. But the real kicker here is that if I actually ran this using that pure Python program, if I ran the full simulation, I would have actually had to wait 3 years to get the results. That is how slow that pure Python implementation was. So I actually ran it on just a small subset and then just calculated from there, because each day is around the same amount of computation. So this is obviously a huge problem. Like, obviously 3 years is just ridiculous, but even if this simulation took 4 days, that would still be too long. Strategies or any kind of building any type of model requires massive amounts of tuning and experimentation, and these simulations need to run fast, hours, not years. So what went wrong? Well, 3 steps are computationally heavy. We have this return step that calculates the stock's daily returns for the past year, correlation, which calculates the correlation between all those returns, and then the decision step, which uses PCA and linear regression to perform that residualization process I talked about earlier. Now, to put it in concrete terms, I calculated by hand the amount of floating point operations that would actually be required. And to do the full simulation, the return step is not that much, but the correlation and decision steps are truly huge. And this is because a lot of them are using ON squared, ON cubed algorithms. And so the total operations is about 200 million, which is a lot. So when we break this down, we see that the return step takes half a day, and then the correlation decision steps are really where it starts to slow down. Now, I'm not going to go into too much detail on why Python is so slow, but the primary reasons are it's dynamically typed, which means every single floating point operation you do requires probably a dozen more operations because it doesn't know the types in advance. It's interpreted, not compiled, which means that the compiler can't optimize anything in advance, and it has fragmented memory access because the lists in Python store heterogeneous types. It can contain different types in the same list, which means it's actually a list of pointers. So you have loads of memory indirection, and you're kind of like throttling the cache, basically. So how can we do better? And this is where Numpy comes in. So again, Numpy is the fundamental package for high-performance computing in Python, or number crunching. There are a lot of other libraries as well, but Numpy tends to be the one that's used the most, I'm sure, again, as you're aware. And really, the key reason why it ends up being so much faster than pure Python is because it has this multi-dimensional array object that stores everything in continuous memory buffers, and then it has heavily optimized C routines to operate on those buffers on the C level, avoiding any Python code whatsoever. So if we look at this ND array class, this is a class that represents any n-dimensional array. It's a fixed size. Elements must be the same type, which simplifies and optimizes a lot of things. So to give you an example, if we call mp.arange to generate this array of 9 elements, what it actually looks like in memory is this. So we have this memory buffer, and then we have a bunch of metadata fields that actually describe how to tell NumPy how to navigate the memory buffer to get the data it needs. So this memory block is just a block of 9 float 64s. The shape parameter tells you the size of the array or the size of the data in the buffer, and the strides parameter tells you how many bytes to move along the buffer to get to the next element. And actually, these shapes and strides parameters allow you to do very interesting things. For example, just calling a reshape to change this 9-sized array into a 3x3 matrix requires no copies. It's actually just changing the shape and strides parameters. What's happening is it just changes shape to 3.3, changes strides to 24.8 to say move to the next row by moving 24 bytes in this flat memory buffer, and then move 8 bytes to get to the next column in that particular row. So you can do loads of things. That you can slice out particular dimensions. You can, you can sort of iterate every 2 rows or whatever. And the key thing here is when you're doing all these types of operations, these reshaping and slicing operations create a view. They don't actually copy the data, which in this example doesn't matter. But if you've got an array of 9 billion floating point numbers, all this starts to add up. So the performance benefits are that data is stored contiguously, so there's no memory overhead. You have cache locality because everything's compactly put together. There's no copies for common operations. And again, these memory buffers that are stored basically in the C level in NumPy, there's very fast NumPy operations for operating on those without even touching the Python level. So just a basic benchmark of adding 10 million numbers. If we use a list comprehension to add two different 10 million number arrays in pure Python, and then in NumPy, we create 2 NumPy arrays. We can either loop through the arrays and then just one by one calculate the result, or we can just use NumPy's built-in addition operator, and we see this is the timings we get, and this is on just the Macbook that I have. So 1 second for Python. NumPy with the looping takes 3.4 seconds, and then the built-in NumPy takes 0.03. So the built-in operator is 36 times faster. Now, what's interesting here, this isn't surprising, NumPy is obviously faster, but what's interesting is that the NumPy with the loop is slower. In fact, it's almost 4 times slower than the pure Python implementation. And this is because when you're explicitly looping over NumPy arrays, you've basically lost all the benefit of actually using NumPy or any of these libraries in the first place. So if you imagine that this for loop, every single time we're retrieving an element from one of these NumPy arrays, we're going into the C level, we're going into that memory buffer, and then we're copying it out as a Python integer in the Python level. So we're actually doing 3 copies for every iteration there. And if you're iterating over 10 million numbers, that's 30 million copies, plus you've got all the function call overheads of calling get item on the NumPy arrays every single time. Now, the real way to use NumPy in these types of libraries is to try and push all the computation and all the looping into the NumPy level. So here we have C equals A plus B, and that's just one function call in Python, and everything else is run in the NumPy layer. And that means you're removing any potential Python overhead. So the key here is you keep it in NumPy. You don't loop through these arrays, and you move the computation to the native level where possible. So when we use NumPy for the trading simulation, just to give you a recap, these are the 3 steps that were computationally heavy in the simulation. If we focus on the first step, we don't have time to cover how NumPy is used in the second and third steps. This first step is quite simple. All we're trying to do is calculate the stock's returns for the past year. Now, the returns here that we're using are normalized, so we're using the percentage return. So this is today's price minus yesterday's price over yesterday's price. So you get the percentage change from each day, what the price of each stock is. So as an example, for Apple, if we wanted to calculate the returns on the 2nd of August, we simply say 155 minus 148, which is the price from the previous day, divided by 148, and you get 4.7. So the return is 4.7. It's increased by 4.7. So if you bought it the day before and then sold it the next day, you would have made 4.7 profit out of it. So we need to calculate this return for all stocks on all days. We could use a nested for loop for stock in stocks, for date in all the dates that we want to calculate the returns for. But of course, as we've established, that's slow. Lots of copies and slow operations are being run in Python code. So instead, what we're going to do is use Numpy to compute these returns. We're going to pack all the stock prices for all the dates in one compact matrix, and then we're going to perform bulk operations on this matrix. So if you imagine this stock price matrix, where one dimension is the stocks, and the other dimension is the date, then what we want to do is take this matrix of prices and dates, NANDs where you don't have any pricing information, and you want to calculate as a returns matrix where each cell represents the change in price from the previous day. So essentially what this means is to calculate this cell, this red cell on the right returns matrix, we're just taking that the same cell in the same in the pricing matrix and the previous cell on the previous date to compute it. Now again, instead of manually calculating each cell with a for loop, we're going to use these bulk operations. So we take our prices matrix, we shift it by moving all the prices forward once to get yesterday's prices, and then we look at our returns formula, and instead of substituting each individual cell into the formula, we just substitute it with each matrix. So we just do pricing matrix minus yesterday pricing matrix divided by pricing matrix. And then all the element-wise operations will happen in the C level. And that will give you back your returns matrix. And the NumPy code for this is incredibly simple. This is a really basic example, but you can take the pricing matrix, you can initialize it as an array of all zeros. The shape is the number of dates in the simulation by the number of stocks in the simulation. Then you populate it using the CSV files that I showed earlier. You compute yesterday's prices with this shift prices matrix, and then you just run the returns formula on the matrices. So you see, the key here is this doesn't have a for loop, and the previous thing had a for loop. That's really all you need to know. And by this not having a for loop, it means you're avoiding any kind of Python inefficiencies. And when we do this, we change this from 462 minutes to 8 minutes. So we've actually arguably made the code even more concise and simple anyway, but also we've just made it tons faster. So it's a 79 times speed up. Now, we can use these steps to perform similar optimizations on the correlation decision steps. And when we look at that, we take it from 3 years to 2.8 days, so it's 390 times faster just by using, instead of Python for loops, you're using NumPy arrays. The key here is the reason NumPy is so much faster is that there's no extra memory overhead, there's minimal copying, it's cache friendly, and again, all these operations are executed in compiled code. So by expressing data in this vector matrix form, you open up a whole new world of optimizations. And this is essentially called vectorization, or at least in Python world, this is called vectorization. The vectorization in Python is the process of rewriting your code to express all the calculations in array matrix form so you can utilize all of these C libraries. And this is often easy to do. Like in this example with the returns matrix, it was very easy to just rewrite it using NumPy, but it's not always. You might need to completely redesign your algorithms in order to vectorize them, and it's actually non-trivial to do so. And also, not all our algorithms are actually vectorizable. Some of them inherently need to depend on states on like a previous loop iteration, in which case you can't vectorize. So here we see, this is the times that we currently have now after applying NumPy. The decision step is still really slow. So this is still significantly slower than the others, and this is because there's some non-vectorizable components in this particular step. And this is where number comes in. So the problem we have is that not all algorithms are vectorizable, and we still have some unvectorizable code that we haven't optimized and is running in pure Python. The solution is to compile non-vectorizable Python code to native machine instructions, and we can do that using numba. So numba, basically, it just allows you to annotate Python functions, say, compile this as native machine code, and it will do so for you automatically. So if we consider this example, let's just assume that Python's built-in sum function doesn't exist for the purpose of the demonstration. But suppose you wanted to sum an array, and you just had a function to do so. You have an array, you have a result value, and you're just iterating through and adding all the numbers together. Now, if you just import the JIT decorator from numba, decorate the function with JIT no Python equals true, telling numba you must compile this as native machine code, and if you cannot, raise an exception. We get this difference. So it's 1.7 seconds in Python and 0.0065 seconds in numba. So you get a 270 times speed up just by adding @JIT. Now, numba needs to know the types in the function in order to know what types to use in the native compiled machine code. Because compiled code, the types have to be static. They have to be known in advance. So it uses the types of the first invocation of the function in order to determine what the types will be. You can also explicitly specify them. So here you can say, well, JIT the function, but make sure that the return value is an int64 and that the input array is an array of int64s. The key here is that this is not magic. It's cool that we can increase this one function by 270 times, but you're really restricted in what you can actually do in these routines. So as soon as you put no Python equals true in that decorator, it will raise an exception if it cannot compile it to machine code. And that means that actually you're very limited in the types of Python features you can use. So you can't just import any Python library and just use it magically. You can't do some of the crazier, more things that you would generally do in like a dynamically typed language. It's really only intended for optimizing these compute-heavy functions. So if you have these small functions where you've got really hot loops, really heavy loops that are iterating like 1 billion, 2 billion times or something like that, it's really meant for those. So it's not going to help. You can't just do ActJit on everything and expect it to be faster. So when we use this for the trading simulation, we're adding ActJit no Python equals true to all the functions that do any kind of computation. And just in case we're explicitly specifying the types, because sometimes numbers type inference can be a bit iffy, we get this. So we take it from 2.8 days to 0.58 days. So now it's taking roughly about half a day. And the speed up from the original pure Python implementation is 1,900. So you see on the steps that the returns and correlation step they haven't changed. They haven't actually gone any faster. And that's because they were already running in native machine code because they were just running Python routines. It was all vectorized code that was running in Numpy. Whereas this decision step had some unvectorizable stuff that was running in pure Python. So by adding JIT there, we actually got some benefit. And so you see here we've gone from 2.61 to 0.37. So the point is, in a nutshell, when you're doing this type of heavy computation in Python, try and use vectorized NumPy code where possible. It will probably be faster than even using numba, for example, if you actually just try and express everything in vector matrix form. But often you can't, either because it's very difficult to do so, and there's business limitations in terms of development time, or you just can't because it's inherently an unvectorizable algorithm. You fall back to numba. So the final timings is our pure Python implementation was ridiculously slow. And this is a logarithmic plot, by the way, hence why they even seem remotely close at all. And when we vectorized, we got most of the way there. So when we used NumPy where possible, we got most of the way there, and we very, very much sped this up. But there was still lots of code that wasn't optimized. And so we used numba to fill in the gaps where we couldn't vectorize. So we've taken it from 3 years to 14 hours, and this is just running on a single MacBook Pro. So yeah, that is pretty much the talk. Just to summarize, Python is great for research, but out of the box, Python is slow. There's increasing demands for faster real-time data processing large volumes of data or training complex models, and you can't really use standard Python for this because it's too slow. It's bad for research, and it's bad for production. But you can still use Python, of course, by using these scientific computing packages. The key is knowing how to use them correctly. I've seen a lot of researchers in our firm, for example, who aren't as familiar with how NumPy actually works, and they'll use NumPy just thinking it's going to speed things up, and actually it makes things slower or doesn't help at all. So it's knowing what they're actually doing under the hood, and by doing so, it's very little work to actually use these tools properly to get the speed ups you want. You keep all your computation in native code by vectorizing using NumPy and then using numba to optimize the unvectorizable code. And if that isn't enough, yes, you can parallelize. You try and identify ways to shard your data. You split it up, run it on different machines on a compute cluster. But I kind of urge people, before they actually go too slow, let's try and parallelize, actually trying just using these tools like NumPy and numba to optimize everything in one single process first and see if that's enough. Really all you're doing when you kind of parallelize to a cluster immediately is you're throwing the problem over the wall to DevOps, because as soon as you parallelize using a cluster, then you have all the issues around distributed system guarantees, failovers, all those types of things that you need to deal with. So suddenly, actually, you're making the problem way more complicated when you could have actually just sped it up by just doing number.jit. So just using NumPy and number alone can yield thousands of times speed up. So I encourage you to try these types of tools first. And that is the talk. Thank you very much. Oh, links to the slides here, and also I'll be for the drinks later, so if anyone wants to talk about anything related to optimizing Python, this was just the surface. Feel free to talk to me later. I'm happy to answer anything, or just contact me on Twitter or whatever else. Thank you. Any questions? Oh, yeah. So number any of the normal Python primitives, numba supports. And numba has also built-in support for NumPy, specifically NumPy arrays. So if you pass in NumPy arrays, numba actually has specific optimizations that it can do to NumPy. So NumPy and numba work very well together. Even stuff like strings, it can still be more efficient. But generally, it's really just meant for primitive numerical types and dense buffers of numerical data and stuff like NumPy. That's kind of really what it's mainly for. You can also use other arbitrary types and even specify your own more complex structures. For example, structures that have a mixture of ints and floats and things like that. But generally speaking, it's numerical data is primarily what it's used for. Yep. Sorry, say that again?
SQLite wouldn't be faster than NumPy?
That's a good question. It depends. So, yeah, I mean, that's a bit of a vague answer. So just to repeat the question was, wouldn't using some kind of simple in-memory database, like, for example, SQLite, be faster than using your operations in NumPy? So I guess there's two things there. The first is, it really you're depending on the database implementation. So yes, it might be faster, it might not be faster. It really depends what you're doing, right? If you're saying, will summing a bunch of numbers up in SQLite be faster than, say, using NumPy? I'm actually unsure that's the case because you have a bunch of other overhead because you're communicating with the database is compiling a query, it's having to do something. If you're just having a NumPy do numpy.sum, that's probably going to be faster. Although I admit I haven't done any benchmarks, so that's just purely a guess at this point. The second thing is there's value in using stuff like NumPy and numba. So the second question, actually the second point, our response to that is more, well, why wouldn't we just use C? Because if Python is really slow, then why would we just not use C? Because that will always be guaranteed to be the fastest thing. The reason why you want to use stuff like NumPy and numba is not just because it's fast, but because it's in line with how you're writing the rest of your code. Right? It's Python code. And so by doing it like that, you're making it more maintainable, more easier for other developers to use and things like that. So I think the disadvantages in using something like an in-memory database because you're expressing things in a different way, in a very fundamentally different way, which might not always be possible. So for example, in numba, with the unvectorizable operations, it would be very difficult to do in a database query, for example. So you're kind of representing the problem in a completely different way by doing it with via relational joins and selects and things like that, just for the purpose of speed up. And so what you try and get with NumPy and numba is that speed up, but you also get the fact that it stays true to the convention of Python. Like it's just Python code, right? It's just sequential Python code. So it's easy to understand. Yeah.
It could be a useful exercise to check whether
Yeah.
you can do like a singular value with the composition on SQL table and is it faster than?
Yeah, no, I agree. I think that's a good benchmark. In fact, I think I'm going to test those benchmarks out. So the next time I do this talk, I'm going to have some appendix slides for that. Any other questions? Yeah. Yeah.
Annotation. So is there a way for numba to actually use type hints, regular type hints?
That's a good question. I don't know the answer to that question. I don't think so. The reason why I would think not, at least yet, is because those type hints, inherently, you can specify types that aren't number supported types. Right. So number has its own types in its library, like int64 and all these other native types, whereas a type hint, of course, can be anything. It could be like mapping, str, dict, or something like that. So all those types of things wouldn't be, you can't guess the types of those in your compiled machine code. So I would suspect not, but it might be possible. There might be some plugin that tries to do so.
Thanks. Great presentation, by the way.
Thank you.
And does numba work with multiprocessing?
Good question. So you can, number works with multiprocessing, basically. So if you have, assuming, of course, your problem is compute heavy, and you're trying to distribute, say you've got 4 CPUs and on your laptop or whatever, and you're using multiprocessing, and you're setting the process pool to 4, you could easily just have a JIT optimized function in number, and have that run in these different processes. That's totally possible to do.
Okay. Thank you.
Oh, there's a question over at the back.
What operations does numba support? Just the arithmetic ones, or numpy, or?
Got it. So arithmetic, obviously general logic stuff. Anything NumPy related, it tends to have out-of-the-box support for. It supports operating on arbitrary structs. So if you imagine some kind of composite type where, like a person, where you have int age and float average score or something like that, I don't know. But you have some kind of composite type, it supports those types of things out of the box. Yeah, basically, usually it's anything that's I/O bound, or anything that uses stuff like generators or function callbacks and things like that. Number tends to fall down on, because of, you have this notion, because all those are executed in Python using dynamic, taking advantage of the dynamically typed nature of the language, whereas number can't do that. So really, any arithmetic operation, any logical operation, and any operations on plain old data structures, just basic densely packed data structures, it works fine with. But anything else, you kind of lose some of the benefits. One thing I didn't mention as well is that number doesn't, it's not, like I mentioned that it's super, super strict in what you can do. So number actually has different modes of compilation. So the no Python equals true means it must compile to native machine code. So everything needs to be very basic. You can only do very restricted things in it. But if you don't specify that, then actually number has this notion of, if you just jittered all the functions in your library, the things that it couldn't optimize, then it will just won't optimize it. So it will just leave it. So often what you can do is you can just see if you jit everything in your code, just to see out of curiosity, if jit everything in your code with no Python equals false, which means that it just won't error if it can't compile it, and it will just leave it be the regular Python function, then you can see if you get any speed up whatsoever. So it's kind of a mix of both. So what this means is you can often have, you can just naively JIT things, and then you can kind of you can benchmark after that and profile and see which things were optimized and weren't, and see what things you might need to simplify in order to get no Python equals true. Oh, there's a question here.
No, I just want. You have a question.
Is there a big difference? Is there any difference between using Numpy and Cython?
Good question. So we actually use Cython as well in our firm. So the difference really with Cython and number is that, so for those who don't know, Cython is essentially almost like a pre-compilation step for Python code. So it's kind of like an enhanced Python where there's extra syntax for specifying statically typed things and defining things in such a way that it's compilable to native code. So the idea is you write Python code, and most of it is just kind of regular Python, but you specify, you have these special keywords where you can say, define this function with, or define this variable with this type and things like that, and then just run Cython to compile all that Python source code as native machine instructions. So not really, no. So you won't really get any speed up. The only potential reason to really use number over Cython, so one issue we've just found with Cython is it's kind of infectious. So if you have some code with Cython, it means that when you're deploying your code, you always need to make sure Cython runs. So you've now added some complexity to your build step, and you're also just not using regular Python. So that means any person who comes on board the project, suddenly they're having to know all these different CP_def and all these different kind of Cython keywords, whereas number is a lot less invasive. Rather than just say run Cython on a bunch of PYX files, I think that's the right extension, on these special Cython code bases, it's actually just regular Python, and you can just specify specific functions in one module, which is all regular Python apart from these two, and it will just work out the box. So I think it's, from a performance perspective, Cython would probably arguably be even better because it's forcing you to do everything in native machine code, essentially. But for the routines that it counts, it's often not worth changing your whole module or large parts of your code base to use this domain-specific version of Python and just kind of isolating it to one or two functions. It depends which one. I've got nothing against Cython, though. We use it and we like it.
Thank you. Some last one question? Okay. Donald, thank you very much.
Thank you.